Here are solutions to homework set number 7 for ECE 376 Embedded Systems. This homework set looks at data collection and analysis of data using student t-test. Now, the first problem I'm going to look at is trying to measure the capacitance of a 100 microfarad capacitor. Now, to do that, what I'm going to do is just set up a capacitor going to ground. On your board, there's a 100K resistor. So what I'm going to do is charge this up to 5 volts and then watch the discharge. By measuring that RC time constant, I can tell you what the capacitance is. So here's the setup. I've got a capacitor going from port A pin 1 to ground. That's a 100 microfarad capacitor. I'm going to charge it up to 5 volts and then let it discharge. Now the program I'm using is a logger program. This reads the analog input on pin 0, converts to voltage, and displays it. So that's what's showing up right now. And you can see as I turn the potentiometer, the LED gets brighter and dimmer. The voltage being displayed gets higher and lower. And in addition, so where'd you go? On this program, the logger program, I can sit there and collect the data, copy it into MATLAB. So once this works, I'm reading port A pin 0, switch over to port A pin 1, compile and download. Then what you'll see is on port A pin 1, here's your voltage. Wait for the code to download. Okay, now the code is running. Here's the voltage, currently discharged. If I charge it up to 5 volts, there's these 5 volts. Take the wire off, it very quickly decays down to 2.1 volts and then slowly goes to ground. What's happening is the LED is drawing current. So here you see the LED turning on. That quickly discharges the capacitor down to 2.1 volts, the turn on voltage for the LED. To stop that, I pull that jumper. Now to charge to 5 volts, it slowly decays down to 0. That's by exponential decay. Now for timing, the LCD kind of slows everything up. So what I did is comment out the LCD move, record this, and also toggle port C pin 1. That lets me know what the sampling rate really is. Ideally it's 10 milliseconds, but this code's going to take some time, so to get the timing accurate, I need to measure it. So, doing that, I actually wound up with the sampling rate being 21 milliseconds. Where that comes from is 10 milliseconds is right here. Everything else apparently is about 11 milliseconds. That's found experimentally. Record the data for 10 seconds and then plot it. So here's what data looks like. And again, kind of the way I collect that, going back over here, I set this up to 5 volts. Come up here to the logger, clear the data, take it off, and there's the voltage decaying versus time. After 10 seconds, I copy it to the clipboard and throw it into MATLAB and plot it. So this is what the data plot's like. That's problem number 1, collect the data. Problem number 2, now determine the time constant. Well, this is a capacitor. It's decaying as A e to the minus bt. Taking the log of both sides makes it linear in time. So log of voltage versus time should be linear. The slope is minus b. That's your 1 over RC time constant. So taking my 3 data sets, doing a least squares curve fit, I wind up with the slope being minus 0.108, minus 0.109, minus 0.11. So there's my data. Converting to capacitance, so the slope is B is 1 over RC, actually minus 1 over RC. So C should be minus 1 over B times R. And R is the 100K resistor that's on your board. So if I do that, I wind up with the capacitance being 92, 91, 90 microfarads. That's a little bit wrong. If I use a capacitance meter, it's actually a 100 microfarad capacitor. What that means is that apparently there's extra resistance on the board I'm not taking into account. I can calculate what that should be. If it was 100 microfarads, I basically have a 90.9K resistor. That's the resistor in parallel. 100K is on your board. The 100K resistor is this guy. There's apparently a 1 meg resistor I don't see, and my guess is that 1 meg resistor is the input impedance for the Pico, or the PIC processor. On to problem number 3. In problem number 3, it's try to find the 90% confidence interval for your time constant. Well, if I assume that R is actually 90 kilo ohms, meaning it's the 100K on your board plus the input impedance for the PIC processor, then the value of the capacitance is 101, 100.54, 100. From that data, I can find the mean, find the standard deviation. From StatTrack, I have sample size of 3, meaning 2 degrees of freedom. For 5% tails, the t-score is 2.92. And to show how to find that, go to StatTrack. Let's see, continuous t-distribution. I have a sample size of 3, meaning 2 degrees of freedom. I want the tail to be 5%, meaning I need to go 2.92 standard deviations left and right. So doing that, I get 103 to 98. Now what that does is, since I just took the standard deviation, what I really did is found the 90% confidence interval for the next reading. If I were to take a fourth reading, I'm 90% certain it'll be somewhere between 98 and 103 microfarads. A slightly different question is, what is the actual value of the capacitor? In this case, the more data I get, the better I know what the actual capacitance is. It does have a value. I don't know what it is, but I'm homing in on it as I get more and more data. That's a population question. For populations, you divide the variance by the sample size, or the standard deviation by the square root of the sample size. So if I do that, I get 0.54 for the standard deviation of the mean of the data. The 90% confidence interval is then the mean plus or minus 2.92 standard deviations between 99 and 102. So that would tell me that the actual value of the capacitor is somewhere in this range, with a probability of 0.9. As I collect more and more data, this is going to get tighter and tighter, and eventually I'll have a very tight window pretty much knowing what the capacitor values really is. So that was the first population. Problem 4 is change something. Take the capacitor, flip it around, do reverse polarity, use a different capacitor. The latter is what I used. I took a second 100 microfarad capacitor from the bin and measured it. Took 4 different readings. So here's the voltage decaying versus time. Found the slope using least squares. From that, find the capacitance value. Once I have 3 values for the capacitor, I can find the mean and standard deviation. And again, the question I ask answers whether I do or don't divide by the square root of sample size. If I want to know what reading I'll get the next time I measure the capacitor, in that case, that's an individual. I don't divide by the sample size. So in that case, I go left and right 2.92 standard deviations, because again, sample size is 3, 5% tails has a t-score of 2.92. I'm 90% certain that my next reading will be somewhere between 96 and 97 microfarads. A slightly different question is, what is the actual value for that capacitor? That's a population question. In that case, I divide the standard deviation by the square root of sample size. So the actual value, I don't really know what it is, but I'm 90% certain it's somewhere between 96.2 and 96.8 microfarads. Finally, the last problem is a comparison of means test. A problem with the t-distribution is it only applies to a single population. Well, if I want to compare A versus B, I've got two populations. T-test doesn't really apply. But what I can do is create a new variable W that's A minus B. I now have one variable t-test apply to one population. So for W, the mean of W is just the mean of A minus mean of B. The variance of W will be the sum of the variances. And this is for an individual. If I pick one more capacitor for A, one more capacitor for B, what's the chance that one is going to be larger? That's an individual. That's what I'm doing here. I've got a standard deviation. Then the t-score is what is the area of the tail, or what is this area? To find the tail, I find the t-score. How far is 0 from the mean in terms of standard deviations? It's 4.39 standard deviations away. From StatTrak, I've got sample size of 3 for A and B, 2 degrees of freedom for A, 2 degrees of freedom for B, so roughly W also has 2 degrees of freedom. I've got a t-score of 4.39. In StatTrak, I can say when it's 4.39, find the area of the tail, and it's 2.4%. So 2.4% chance that the next value B will be bigger than A, 97.56% chance A will be bigger than B. A slightly different question is, I've got two different capacitors, A and B. Which one's actually bigger? Well, in that case, that's a population. Their sample size does matter. I have a sample size of 3. For populations, you divide the variance by the sample size for A and B. Get a standard deviation for the for W. And now the t-score is 7.6. Converting that to a probability, the area of the tail is 0.9%, area to the right is 99.1%. So I'm 99.1% certain that A is the bigger capacitor. And this is kind of difference between English and statistics. I'm 99.1% certain that A is bigger. That is statistically significant. I can tell that A is bigger than B. A different question is, do I care? This is the difference between, I think, 100 microfarads and 97 microfarads. For circuit analysis, I don't really care, typically within 3%. That's actually pretty close. That's English, do I care, versus statistics, kind of measure the difference. So the word significant depends upon whether you're talking about statistical significance or engineering significance. But anyway, that's homework set number 7 for ECE 376.